Chapter 10 continued, The Shapes of Molecules, Section 10.3, Molecular Shape and Molecular Polarity. We now should have a sense of the shapes that molecules adopt and why they do so. Knowing the shapes of the molecule will help us to understand the physical and chemical properties of the molecule. The shape of the molecule will allow us to determine the polarity of the molecule. Molecular polarity can influence melting and boiling points, solubility, chemical reactivity, and even biological functions. Recall that bond polarity is a measure of how equally the electrons in a covalent bond are shared between the two atoms of the bond. As the difference in electronegativity between the two atoms increases, so does the bond polarity. In a molecule that contains more than two atoms, both the molecular shape and the bond polarity will determine the polarity of the molecule. A molecule is polar if it contains one or more polar bonds and the individual bond dipoles do not cancel. This is figure 1013, and it shows the orientation of a polar molecule in an electric field. Hydrogen fluoride is a polar molecule because the electrons of the covalent bond are not shared equally between the fluorine atom and the hydrogen atom. Since the fluorine is more electronegative than hydrogen, it attracts electrons of the covalent bond towards itself and away from the hydrogen atom. This result is a partial positive charge on the hydrogen atom and a partial negative charge on the fluorine atom. In the absence of an electric field, the HF molecule are orientated randomly. In the presence of an electric field, the partially positive charged hydrogen atoms orientate themselves towards the negatively charged plate, while the partial negatively charged fluorine atoms orientate themselves towards the positively charged plate. When determining the polarity of a molecule, we must take the molecular shape into account because the molecule may contain polar covalent bonds and still be a nonpolar molecule. For example, let's examine carbon dioxide. Carbon dioxide is a linear molecule that contains two carbon-oxygen double bonds. Each of the carbon-oxygen double bonds are polar because of the difference in electronegativities between oxygen and carbon. However, both of the carbon-oxygen bonds are identical, which means the bond dipoles are equal in magnitude. The electron density models that show the regions of higher electron density are shown in red, are at the ends of the molecule, while the regions of lower electron density, blue, is at the center. Bond dipoles and dipole moments are vector quantities that mean they have both a magnitude and a direction. The overall dipole moment of a polyatomic molecule is the vector sum of its bond dipoles. Both the magnitude and the direction of the bond dipole must be considered when summing these vectors. The two bond dipoles in carbon dioxide, although equal in magnitude, are exactly opposite in direction. Adding them together is the same as adding two numbers that are equal in magnitude but opposite in sign, such as 28 added to a negative 28, which will equal 0. The bond dipoles, like numbers, cancel each other out. Therefore, the overall dipole moment of carbon dioxide is 0, even though it contains two polar covalent bonds, making it a nonpolar molecule. Next, let's consider water. Water has the tetrahedral arrangement and the bent or V-shaped molecular shape. Water also contains two identical polar oxygen-hydrogen bonds. The bonds are identical and the dipoles are equal in magnitude. However, because the molecule is bent, the bond dipoles do not directly oppose each other and therefore do not cancel each other out. This means water is a polar molecule. Molecules with the same shape may have different polarities. Let's compare carbon tetrachloride, shown on the left, to chloroform, shown on the right. Both of these compounds have the tetrahedron geometry, but only one of them is polar. In carbon tetrachloride, all of the carbon-hydrogen bonds are polar, but the individual bond polarities cancel. With chloroform, the bond polarities do not cancel, therefore this molecule is polar. So how can we tell if a molecule is polar or not? For all AXN molecules in which all the X atoms are the same, certain symmetrical shapes such as linear AX2, trigonal planar AX3, tetrahedral AX4, square planar AX4E2, trigonal bipyramidal AX5, and octahedral AX6 must lead to nonpolar molecules even though the individual bonds might be polar. Sample problem 10.9 wants us to predict the polarity of three molecules: ammonia, boron trifluoride, and carbonyl sulfide. What is our strategy for solving these problems? First, we need to draw the Lewis structure and name the molecular shape and mark each bond with a dipole arrow. If the compound has one of the symmetrical geometries we mentioned on the previous slide, and if all of the atoms surrounding the central atom are the same, the compound will be nonpolar. If the compound does not have one of the symmetrical geometries, or if it has a symmetrical geometry where the surrounding atoms are not the same, the compound will be polar. Please work through this sample problem on your own before moving on to the next slide where you can check your work. Here is the solution for ammonia. Since ammonia has the trigonal pyramidal geometry, it is considered polar. Here is the solution for boron trifluoride. This compound has a symmetrical geometry where all the surrounding atoms are the same. Therefore, it is nonpolar. Finally, here is the solution for carbonyl sulfide. Even though the geometry for this compound is linear, the atoms that surround carbon are not the same. Therefore, the individual dipoles do not cancel, and the compound is polar. Here is figure 1014, and it illustrates the influence of atomic properties on microscopic behavior. This is the end of the material we will cover from chapter 10. Please work as many of the end of the chapter problems you feel is necessary in order for you to master the concepts presented in this chapter. When you are comfortable with the material, please take the weekly quiz. Then work through the weekly laboratory assignment and then take the laboratory quiz. After you have completed the laboratory quiz, please proceed on to week 15. Week 15 will cover the material presented in chapter 11 titled Theories of Covalent Bonding.